Hey everyone, let's dive right into this explainer. Today we're looking at something we literally encounter every single day, sugar. But I promise you, we are going to completely change how you see it. We're going to trace its path from some visually stunning and honestly slightly gross kitchen experiments into the sterile environment of a lab, deep into our own metabolic pathways, and finally, we'll watch how it transforms into a mesmerizing geometric gemstone.
Here is our roadmap for today. We're going to cover the soda science experiments, measuring hidden sugar, cane sugar versus corn syrup, and finally, growing giant sugar crystals. Let's get right into it.
All right, Section 1, the soda science experiments. Let's take a look at some of its physical properties. So consider this visceral question from kitchen scientist Nanny Anita over at the My Baba blog. What actually happens when you boil a pan of Coke? I mean, we're so used to just drinking this stuff ice cold, right? But applying extreme heat or even introducing foreign objects to it reveals a lot about what we're actually putting into our bodies.
Nanny Anita did some pretty wild kitchen experiments. Check this out. First, if you leave an egg fully submerged in Coke in the fridge, the shell completely dissolves after just 1 week. No joke. Then, if you pour that Coke into a frying pan and boil the water out of it, you're left with this bubbling, gross, tar-like substance. It's essentially just burnt sugar and syrup. But the wildest one? Mixing ordinary milk into a bottle of Coke creates a super vile, curdled reaction. And this reaction happens right inside the bottle. Here's why. When you add the milk, the soda's high acid content immediately makes it curdle. Specifically, the phosphoric acid molecules in the cola bind super tightly to the milk molecules. This chemical bonding makes the molecules way denser and heavier. So heavy, in fact, that they literally sink to the very bottom of the bottle over a few hours. What you're left with at the top is this completely clear but very unappetizing liquid. Moving on to Section 2, measuring hidden sugar. How do scientists actually figure out how much sugar is hiding in that tar-like syrup?
Well, according to a really interesting study published in the Journal of Clinical Case Reports, Medical Images, and Health Sciences by researchers down in Nigeria, scientists has a very specific and actually pretty elegant way to quantify this hidden sugar. They aren't just guessing, they're using the laws of physics and mass.
So here's how they did it. First, they let 7 different cola brands degas for 2 hours, basically just letting them go flat. Then they measured the exact mass of 100 milliliters of each one. To get a baseline, they dissolved known amounts of pure sugar crystals into distilled water. By mapping the mass of those pure solutions against their densities, they created this perfect straight-line graph. From there, it's like a giant puzzle piece snapping into place. They just take the density of the flat colas, trace it on that graph, and boom, they can accurately measure the exact hidden sugar content.
The results? Actually, pretty surprising. They found that while major international brands, think Coca-Cola, Pop-Cola, and Pepsi-Cola, contained the exact sugar amount claimed on their nutritional labels, other untested local brands showed some really significant discrepancies. It really highlights why independent scientific verification is absolutely crucial. Okay, Section 3, cane sugar versus corn syrup. We know how scientists measure the volume of sugar, but how do these specific sweeteners actually behave once they enter our bodies?
Let's start with cane sugar. Made straight from sugarcane, this is a natural sugar containing sucrose, which is a perfect 50-50 split of glucose and fructose. As CCS Medical points out, our bodies break this down extremely fast. It sends glucose rushing straight into the bloodstream, and that causes a really fast spike in your blood sugar.
On the flip side, we have high fructose corn syrup, or HFCS. You'll find this in almost all sodas made in the US, mostly because it's a much cheaper, corn-based alternative. But unlike cane sugar's valence split, HFCS packs a significantly higher concentration of fructose. And our bodies process these two very differently. CCS Medical impartially notes that HFCS is primarily processed right in the liver. Consume it in high amounts, and it may lead to faster fat storage and insulin resistance over time. Cane sugar, meanwhile, has a slightly more balanced makeup and is processed a bit more naturally, potentially easing the burden on the liver. But, and this is a big but, the medical consensus remains clear. Both of these sweeteners will rapidly spike your blood sugar, and both require real caution.
So for anyone managing diabetes or really just trying to regulate their blood sugar, CCS Medical's advice is incredibly practical. First, limit your regular soda intake, even the natural kinds. Hydrate with water, diet sodas, or unsweetened tea instead. Always read your labels so you know exactly what kind of sweetener you're dealing with. And hey, if you really just need that soda craving satisfied, a clever trick is to mix half a glass of soda with sparkling water. You instantly cut your sugar intake in half, but you still get that satisfying fizz. All right, let's pivot to section 4, growing giant sugar crystals. We're moving away from metabolism to look at the sheer aesthetic beauty of sugar.
We're going to learn how to replicate its crystalline structure at home using a fantastic guide from a university student named Chase over at Crystalverse. The whole trick relies on creating what's called a super-saturated solution. The idea is simple, but honestly, so fascinating. Hot water can dissolve a massive amount of sugar, way more than cold water. So you heat the water, pack it full of sugar, and as it cools down, the liquid literally can't hold it all anymore. That excess sugar is forced back out, and as it leaves the liquid state, it forms these incredibly beautiful structured crystals.
If you want to make simple rock candy, you just mix a heavy 3-to-1 ratio, 3 cups of sugar for every 1 cup of water, in a pot. You heat it for just under 10 minutes until that cloudy liquid turns clear. But watch out, turn the heat off immediately so it doesn't caramelize. Let it cool completely, pour it into a jar, and then drop in a wooden skewer that you've already rolled in dry sugar grains. Those dry grains act like little seeds. Leave it overnight, and massive clusters of sugar crystals will grow right onto the wood. It's like magic.
But what if you want to grow a giant, perfectly transparent geometric gem? Well, for this, you pour the solution into a flat dish and hide it away in a drawer to shield it from any moving air. You patiently wait a few days until a single, perfect hexagonal crystal forms right on the surface. Now, to make sure it doesn't grow hollow, you have to delicately sink it to the bottom by dripping solution right on top of it. After that, completely seal the dish in isolation for up to a whole month. Because there are no other crystals competing with it, it'll grow into this massive clear gem.
Now, Crystalverse has one major warning here. You absolutely cannot touch the crystal while it's in this super-saturated state. If you try to nudge it with a spoon or your fingers, you're going to chip it. And that one tiny chip releases thousands of microscopic particles into the solution, creating what they call sugar dust. This dust acts like thousands of tiny new seeds that'll stick to your beautiful transparent gem and completely ruin the whole batch. So hands off.
So think about everything we've uncovered today, from boiling down into a bubbling tar in a frying pan, to being elegantly graphed by scientists, to how your liver chemically processes its different forms, and finally, how it can be coaxed into these fragile, perfect geometric gems. How are you going to view this powerful carbohydrate tomorrow? The next time you take a sip, remember, you aren't just tasting sweetness. You're interacting with one of nature's most fascinating and multifaceted molecules.